joined in 2000 Intel or Infineon at that time, and he now heads at Intel group that does the advanced algorithm design, correct? And that gives another perspective. We've seen the exciting perspective from the tool design and the close interaction with the actual layout people, and now we see another perspective from the algorithm side. And not the analog one, but the digital world. Okay, please.
Okay, thanks a lot. Yeah, so I just flew in from rainy Duisburg, Germany. That's where my site is, and ended up in sunny workshop of Professor Meyer, and that reminded me of a occasion 5 years ago in Chateau St. Gerlach, MP-SOX workshop. So workshop on microprocessor systems, and this was exactly the same experience. I drove away from, in the time it was not so distant, rainy Duisburg, ended up in sunny Netherlands, and we had a very enjoyable workshop. And yeah, because of that, I just was asking, that's 5 years ago, yeah, what has happened since then, and how have our problems changed? Yeah, so at that time, well, we were not really doing good at Infineon, yeah, so we lost our prime customer Siemens at that time, and we had just finished our first 3G platform, and we were feeling like the kings because the hardware was working. We were done with our part of the verification. Yeah, and actually I was looking forward to have really enjoyable week at the workshop. Yeah, but then the customers started ramping the products, and suddenly you have millions of your platforms out there, and you start to anticipate new problems. And it took more than a glass of wine for me to get relaxed at this workshop. Yeah. So what I want to do is really always also taking this perspective of what has happened in the past 5 years. Again, for those who are not so acquainted with wireless talks, just briefly show you what I'm doing and what this is about. Yes, what has happened in the past 5 years? How do I rate our design decisions with respect to that? How would they change, or how will they change? Then how does the type of baseband ICs I'm involved with, how does it look? Yes, and the biggest topic really for me is verification of this cellular stuff. And I don't have the answers, yes, so I would be happy to get some inspiration here. Okay, so I'm working at Intel in the meanwhile, so as probably some of you know, my group, or the wireless group of Infineon was acquired by Intel, which itself had already pretty big wireless activities. So the things we are focusing on are really the slim modem platforms, so the cellular modem platforms, covering everything from RF to the protocol stack. And of course, there's much more to mobile devices, and Intel is becoming a big player in that. The main sites in Europe doing that is Munich, of course, the former Siemens site, Duisburg, that's us, and also Nuremberg, where the protocol stack eyes are, Dresden, and Aalborg, Sophia Antipolis. So that are the European activities. So if you look at the mobile phone platforms, it's pretty much exactly as Mr. Kunkel has told us. Yeah, we have a lot of standard blocks which are connected. In our case, the magic spice is pretty big still, the spice part. Yeah, so we have a lot of standard blocks, like also the connectivity to the outside. And we are glad to have good IP providers for that kind of stuff. So one less thing we have to worry. On the one thing connecting us to the real world, we have the analog front, we have the RF chips. On the other side, we have the application processor. Yeah, so this is where the user comes in with his real life. And then other things, of course, which takes a lot of room, are connectivity, positioning, IP and chips, power management and memory. And okay, the way you integrate that, it's differently. Yeah, so we really have some devices where you have more or less all of this on one chip already. But if you look at the high end, then this cellular baseband is still so complex and becoming such a differentiator that typically you have still a separation of cellular baseband chips, RF, and application processor. This cellular baseband processor, which then implements the wireless signal processing and the wireless protocol stacks, that's what I'm dealing with. And what are the key challenges for that? Yeah. So the first one sounds trivial, but it is not. Just delivering the correct functionality, yeah, at the system level. Yeah, that's still the main thing we have to fight with. Yes, and if we can trade area for it, can trade power for it, we would eventually go for it. Yes, if we are able to deliver this just the right functionality at the time that the customer wants it. But of course, he still wants best-in-class performance, so signal processing is still a differentiator. But we have to provide lowest power consumption. So having the functionality is your door opener, yeah, but then your benchmark on power consumption, on lowest PCB area, making it smaller so that you have more room for batteries, and also enable the overall smallest cost position. Yeah. That's the smallest amount of bill of material. But if you go, for example, in RF and look at LTE, you have so many different spectrums, and you have to look at that. For example, calibration is now really getting a big problem for manufacturing. Calibrating a mobile phone in production should take seconds, not minutes. And that's also very big, becoming a very, very big differentiator at the moment. Okay, so what are the trends? So I try to keep that one short. Of course, mobile communication is not about phones anymore. It's really about mobile computing. And this affects, of course, the use cases we have to deal with, yes. Also in terms of power consumption. So in the past, for example, standby time was very, very important, yeah. But now people are really using the big bandwidth that we can provide theoretically. And suddenly people see, okay, power consumption in active mode is really becoming a big problem. And then we have a big difference on how the wireless markets develop. So Europe is actually quite easy. Yeah, we have very major markets, and everybody's sticking to the standardization. We have sufficient spectrum in most of the countries, a little fragmentation, and also we have the operators are not so nasty. Yeah. They are not having such aggressive campaigns on the quality of the networks, and this is also making our life simpler. In the US, it's just the opposite. The spectrum is completely fragmented, different spectrum anyway. You have only small chunks of spectrum. LTE should be operating at 20 megahertz, but some operators only have small chunks, and they need to scratch them together somehow, but there are different bands to get their bandwidth. And then that's one of the main challenges in the US. And then you also have still different radio access technologies, and you have also operators who try to get their special flavor and also use that in marketing very aggressively. So it's not like in Europe you do whatever 3GPP tells you and you're happy. There's more push coming from operators. In Asia, you still have these local radio access technologies, TD-SCMA, although this is the main pusher for LTE TDD mode. And one special thing also in Asia, I don't know exactly what they do, multi-SIM, having several SIM cards in one phone and being able to have contact to different operators at the same time in different radio access technologies. It has to do with sometimes with the coverage of networks, yes, but it has also to do with accounting models. This is something coming from Asia. And other big trend is standardization. So the innovation here is really killing us. Yeah. So you get in all radio access technologies, of course, LTE, but still 3G and even 2G, you get innovations. Almost at a yearly pace, you get new standard releases. And we have to provide, or we have to support most of that. You have femtocells, Node Bs, getting more popular, so new scenarios we have to deal with. And you have then lots of advanced technologies being designed into the networks. MIMO, we need interference cancellation or avoidance technologies, and also cross-layer interaction, so between different physical layers. And yeah, this is really very, very brutal speed we have to deal with here, and it's almost killing us. Yeah? So what does this imply for the baseband technologies? So obviously we need to squeeze more and more different functionality in one chip. And 5 years ago we were thinking, okay, in 5 years from now, yeah, we are 3 technologies further, and so die area and logic gates is not so much of a problem anymore. And probably we will go for some software-defined radio. Power consumption is not so much of a problem anymore. Definitely, this has not happened. Yeah, so we have to squeeze so much functionality in, and this multi-SIM problem really also spoils the party for sharing resources between RADs. Yeah, you have to really establish 3G and LTE connections in parallel, for example, on one baseband processor. Then we have to do all this signal processing stuff. Yeah, at first you say, yay, I have a lot of gates. Yeah, but the problem is now you also have to use them. Yeah, because the competitor is also using them. And if you don't do innovation, the competition will do the innovation, and then you're in big trouble. Yeah. So Shannon still beats Moore to have this slogan, and but the biggest problem is actually the control flows, not the signal processing, but the permanent reconfiguration of our platform, of the operation modi. This will further aggravate, in particular with all this smart interference avoidance stuff. Yeah. So my conclusion is basically the architectures we are having are still valid. Yeah, and also if you talk to guys you know in the industry, it's pretty much that you still have a lot of dedicated data path architectures in this type of ICs. But of course, increasingly more software and firmware, because you, of course, need to be able to really adapt to the changes. Yeah? So baseband architectures and verification, that's my main topic. So yeah, if you look at the way the modems are designed, as I said, we still have data passes, and so we have, these are basically targeting at the signal processing, number crunching type of stuff. Yeah, you don't want to do a FFT in software, you don't want to do bit operations in software. So for example, an outer decoder, I hardly believe you can do this in software efficiently. Yeah? And so that's where you typically have a lot of dedicated hardware again to meet power and area targets. But we are also using DSPs and ASIPs where you need more flexibility. Yeah? So you try to restrict the dedicated hardware to what you assume is really fixed. So the modulation, demodulation part, or equalizer hardware. But the parameterization, estimation, equalizer coefficients will be done softer. Then you have the modem control firmware. So this is one, we have a lot of timing critical procedures like power control. We permanently have to react to changes in the network or in the environment, like you drive through the landscape and one base station disappears, the other turns up. Yeah, and then the whole modem has to be reconfigured to deal with that. So that's done naturally in software, and for that we have embedded microcontrollers. which have then the real-time capabilities. And on top of this, of course, you have the protocol stack, which implements all the higher layers. And that's actually containing the most functionality. But it's, of course, very much standardized. So it's pretty clear how to do that. There's a little area for differentiation there. But you have to deal with a huge complexity. That's what basically runs on standard microcontrollers. And here the main criterion is really performance and keeping the overall complexity low. So this is how this maps to an architecture. Yeah, so you have your protocol stack software, which configures your modem, here. Yeah. Then you have your firmware, which runs on real-time microcontrollers, and you need to define some interfaces which then still can comply with real-time constraints. And these configure processing elements, whatever they might be. Yeah, it might be dedicated hardware, it might be DSPs or DSP clusters, whatever, to do the processing. Yeah, and on the one side, you connect to the AP. Yeah, on the other side, you connect to the RF. The connection to the RF chip. So typically in most devices or in the high-end devices, you still have a separate RF chip. Here we have this problem of the pad limitation. Yeah, so you cannot have deliberately many pads to connect for GSM, LTE, 3G, TD-SMA, you name it. You can't have a dedicated pair of pins for each. And you have a lot of control going on. So also there you have serial interfaces, which have, of course, some effects on sharing this serial resource. So you have a complex programming interaction between baseband and the RF chip. And that's the type of system we have to deal with. And the complexity really doesn't lie in the number of gates we have. It lies in the interaction of all these blocks here with real-time constraints. So the type of thing is, like in 3G, you have continuous transmission. Yeah, that's easy. So you always do some coding, you transmit it, and at the same time, you have continuous receiver. You do demodulation with your smart algorithm, then channel decoding also with your structures. So that's a simple, steady state. Yeah. But of course, that consumes a lot of power, so you want to interrupt that. Yeah? When you interrupt it, what you have to do is you have to start your channel coding, your transmitter. You have to tell the RF to shut off, but exactly in the correct moment. And the same thing on the receive side. And having the right timing in these operations and making it consistent in all situations which you cannot anticipate, that's really a challenge. So for verification, we follow the V model. So verification approach. And I want just to tell you how this maps to our mobile phone platforms. So in the beginning, I mean, what the customer wants is some functionality. Yeah? He doesn't want hardware. He doesn't care what architecture you use. He wants some functionalities, and he wants you to meet some KPIs. Yeah? So this is where it starts. Yeah? And in the end, you have your solution, yeah? And you have to see, does it really do what I originally intended, and will it fulfill the customer requirements? Yes, and I'm working in system engineering. Yeah? So we break these requirements down into architecture decisions. We develop algorithms, but also the architectures behind it. And then these architectures, for example, together with the firmware which runs on it, later has to be checked against the firmware which has been implemented, the hardware which has been implemented, and which runs together. Yeah? So this is a second layer of verification. And down here, yeah, when it comes to RTL design, this is what we all know well. Yeah? You design some RTL, yeah? And then you do some pre-silicon testing, yeah? And the equivalent then on the other side of the V model is the production tests. That's the cadence that you go to. First you design it, yeah, and try to as many of these steps pre-silicon, of course, yeah. And in the end, you verify whether you were successful. And so what we are acquainted to is algorithm simulations to keep the 3GPP standard requirements, and we match these again against our RTL designs. Yeah? So this stuff here the pre-silicon verification works pretty well. But at this level already, yeah, what we use the only thing we can use is the virtual prototype. Yeah, that's the main vehicle for that. And but here already the system complexity becomes so large, yeah, that it's very hard to achieve sufficient verification here pre-silicon. So just going shortly through hardware verification. So I see I have some color problem here. So what we do is we develop our data flow models which comply to the 3GPP standards. Then we match it to the VHDL description of what we want to do, and if it fits, then we are happy. And these are really limited amount of designs, results that you can get here. As we go for systems on a chip, yeah, then we have a lot of combination of such blocks. But still here, by choosing appropriate architecture, we can still limit the number of use cases which you have to check here. Then in the end, of course, we do also simulations in VHDL comprising software and firmware to have some coarse check. So this is really thanks to the advance in the EDA industry. We have really very mature technology here, and also the computing power today enables us to really verify the complete digital part of the systems on a chip with a very good technology, and typically that's not blocking. Yeah? So it's still a challenge, yeah? And I'm really thankful we have the EDA industry, but it's really mature now. Yeah? But what does this really mean then in the end? Yeah? So we have now tested our signal processing capabilities. We know our hardware is working. Yeah, and then the stuff comes back into the lab. And what the management wants to have is the first call. Yeah? They want the device should work, and you connect to the network, and you say, hello, Mr. Oil, or whoever, you call your CEO and say, yeah, the platform is working. Yeah? And everybody's looking at that, and if you have done this, you're really a great guy. Yeah? But this is just a start. Yeah? So if you have done this one, the next stuff which will happen is you have to pass your GCF tests. So this is the type of tests which are specified by the CGB standardization, and think, okay, when I pass that, then I have a good device. But it's still not the case. Yeah? The next step is IoT. You go to all the operators, yes, and every network equipment vendor has a slightly different interpretation of the standard, and this is when you discover, okay, the world is big, and the standard is not so precise as you have thought. But the real shock then comes in real life, yeah. So that's when you drive through the networks, and you get the real network setups. Nobody is really sticking to the 3GPP requirements for setting up their network, and you can go there whining and say, well, they are sticking not to the rules. Yeah? They will just say, well, this is a competitor device, it works, yeah? You better also work. Yeah? And that's what we go through. And okay, this was a display in dB. So if you go to percent of coverage, then you really see, yeah, when the management applauds, yeah, you have seen nothing of your functionality yet. Yeah? And also, CGP, GCF, and IoT will not give you a lot of coverage of your problems. This really just happens when you look at the real life scenarios. Yeah? And this is what is really scary. Yeah? On one hand, you have an innovation cycle of 1 year. Yeah? On the other hand, it takes you almost a year to verify your systems through all these steps. So naturally, you have to be able to do more in pre-silicon here. Yeah? Okay, so we think that the link level simulation really only, and the hardware verification, covers like 5% of our problems. So how do we get from this 5% to 100%? Actually, there is no solution for that. Yeah, but the question is how you can at least improve. So this is our 5% of functionality coming from the 3GPP specifications. Here we have our real system. Yeah, how do we bridge that so that we conform to all that, to all physical procedures, dynamic reconfigurations, and all the things that happen in reality. So up here it's an algorithm model, and down here the only thing I can think of is a virtual prototype. So what is the virtual prototype? I guess more information here than I anticipated. So it's really an executable specification of your hardware implementation. Yeah, so here also we have some third-party models for whichever cores we use, which we can simulate at high speed in System C. We have models for our bus systems. We have models for some dedicated control hardware. And in there, we plug in our data flow simulations to serve as a reference for our signal processing. And on all this, we run our real firmware to get to check for the correct implementation. The problem now is, I mean, we really have to address thousands of test cases. And so we need some reference model to compare against, yes? And this has to be as capable actually as your platform, yeah? And also to anticipate all your problems. And this is really the biggest problem we have at the moment, yeah? So at the beginning I thought, okay, we buy some test equipment from Ode and Schwarz, yeah, and they will test it, yeah? But they also basically cover these 5%, the first 5%. So what we have to do is really, we have to spend huge efforts in coding these scenarios, giving reference test cases to check whether our system is really do what we want to do. And this requires a lot of detail, expert knowledge in the 3GP standards. You have to know exactly what are the corner cases of your implementation that you really check them. And this is very time consuming, and it involves a lot of our expert knowledge from the system side. Yeah? So we are really, very much dealing with this verification instead of doing innovation. And the problem is that what we call BP, it's just the executable spec of the hardware model. But what we actually would need is an executable spec of the system behavior. Yeah? That's actually what is missing here. Yeah? So I have a VP, great, but what can I do with it? Yeah? I can run my firmware on it, and how do I know this is correct? And just to give you a small impression of the type of complexity we're dealing with, I want to give a very simple example. Yeah? It's a small feature called CPC. Yeah? So I already said we had this problem that we have a lot of power consumption in the standard 3G transmission. That is a problem of course, for the talk mode user experience for 3G. So theoretically, even LTE could have less power consumption than 3G. And the idea is then, yeah, why don't we interrupt this continuous transmission whenever we don't talk? Yeah? Or for example, if you have a mobile browser use case, yeah, typically you don't want continuous transmission, more packet-based transmission. So why don't we just transmit this continuous uplink transmission pattern and also define intervals where I don't have to listen in the downlink and can shut off my RF, which consumes most of the power. This was introduced in the release 7 in 2007, and sounds cool. Why don't we have a single network which really does it? Yeah, I mean, it really sounds like a good idea. So again, looking at it, just to give you, it's not so complex. Yeah. So this is what we used to have. We have continuous uplink transmission, yes, and in parallel, you have some bursty HSUPA transmission. So what you then define is, if I have no uplink transmission anymore, I have a mechanism, a counter, which counts for how much of time I don't have a transmission, and I introduce some gaps in between. And if there's really nothing coming for a long time, then I change the gap pattern to become even bigger, yeah? And then as soon as somebody wants to transmit something, I start up anything again, yeah? But that's really not so complicated, yeah? And also, if you look at the, but remember what I've been telling you, yeah, shutting things on and off sounds simple, but can be quite complex in your receiver, yeah? And also, if you look at the parameters, so it's like 10 references or so in the standard document, yes, and you have some parameters defining the activity patterns, yeah, and when to listen, this kind of stuff. For the transmitter side, and you have the same for the receiver side, yeah, also a couple of parameters. But still, then the question is, you have all these parameters, yeah, you have some really simple rules. How do I specify that? And this is where we saw, okay, we must go a different way, yeah. So let's just have a executable specification here. Let's just have a model of this pattern with respect to the parameters and use that as a specification. Yeah. And I thought, okay, it should not be a big deal because the rules are really simple. Yeah. And actually, I have a genius hacker colleague who then wrote a tool, yeah, with graphical front end and everything, just to deal with that pattern. Yeah. So you find all these parameters here. But you see, it's really just sticking to this top-level parameter pattern, so actually not really very complex. And I can then configure my transmission pattern and then get something like that here. So here, for example, you have the EDCH transmission, so the uplink HSDPA transmission. Here you have the CCH, so the uplink control channel. Yeah, and at some point you start with this pattern. Yes, then here comes an EDCH, so an uplink transmission, and you have also to transmit some control information. So works quite well. But as soon as you change the parameters a little bit, yeah, these patterns change completely. Yeah, and they can be, of course, there's a big diversity in that, and like this is very scarce pattern here, and yeah, this type of a model was a huge benefit, of course, for our firmware development, but it covers actually just a very tiny part of the complexity. Yeah, so we have really discarded any signal processing. We have discarded any real-world effect, yeah, like real channels or something like that, and still. Yeah, the total simulator is several thousand of lines. And if you look at the pure functionality, it's still several hundreds of lines of code. And this is really only a fraction. And this is also time-consuming, yeah, cumbersome. And the real implementation, of course, is still magnitudes orders of magnitudes more complex. And what I really find remarkable, yeah, we actually start off with some pretty simple rules here, yeah, and we end up with hundreds of lines of code, and what we're actually missing is abstraction here. So the simulator was not an abstract model, it's really a trial implementation of the scheduling. And if you have to do that with everything, then of course having a reference is not so much fun, yeah, then basically you need a complete second team just for describing the standard functionality. So that's the question I'm asking here, and I have no good answer for that. Is there a way for abstraction of complex systems? So really complementary to what we are doing in our algorithm simulations. So there we have a fixed data path looking at bit error rates, failure rates, so statistical problems, but with very limited parameters and also with very little reconfiguration. Yeah? And here just do the opposite, yeah? Discard any signal processing, but really try to implement the full scope of complexity you have. Yes? So all the tens of channels you have to consider in a downlink, all the different times you can have, having several base stations in parallel, having several users in parallel, and doing all the reconfigurations that can happen in the real world. If I would try to do it the way we do it with the CPC generator, we would end up with millions of lines. And yeah, so that's really, if anybody has, I mean, there should be scientific work on that. Yeah. So I mean, I've had some PhD student who was able to do a little bit of work on that, but you soon start, it's getting really complex. So what we try to do is still have like a graphical approach. We define processing elements, we define channels, and try to define then the scheduling. Actually, what the complicated thing is about is finding the scheduling of all the activities. Try to get an implicit scheduling by defining causality and timing relations, just of the type that you have in the standard. Yeah? And then you have an implicit scheduling. It's a bit like stream-driven simulation, but with timing. Yeah? That's what we tried. But actually, we don't have a real good tool on that. Yeah? And so if there's any scientific work on that you know of, any tools, yeah, or that would be very, very much appreciated, because I think this is really what will distinguish the successful from the less successful mobile phone platforms in the future, handling this complexity problem. Yeah? That basically concludes my talk. To give you a summary again, so I think based on the developments, I don't see a real paradigm change in wireless systems design. I think it's quite mature there, but it's really a quantitative problem of the huge, huge complexity. Yeah, we have so many new features coming in, and they are getting more and more complex. Yeah, so having good signal processing is still a differentiation. Yeah, and also finding good ways for implementing data passes. But really, the verification of the complete system is what is killing us. And the VP, yeah, it's just the beginning. Yeah? It's the first step. It's a tool which enables us to do the verification, but it's really not solving our main problem. How can we really describe the target behavior of these systems and verify them in the end? Okay, then thanks for your attention, and I'm waiting for good proposals. Yeah.
Thank you very much. That was an exciting perspective, and I think the questions which I'm also going to ask at the panel is certainly about the interaction of academia and industry, which used to be great 20 years ago, or 10 years ago. So I'm not asking the question because we stick to the format.